So hello everyone, today I will be presenting about our robot product. This is our name of our project, Swarm Robotics Collective Motion based on the AES model. So this is our group members. My name is Nhiên, and these are the topics that we will be presenting for today. So what we are doing is about Swarm Robotics. This is a field of research where the engineers they will try to mimic the natural behavior of the insects and the animals outside. Here you can see these birds, they are moving in a formation to reduce the air resistance to extend their journey. These ants, they are carrying a weight that is multiple times heavier than their original body mass. These two scenarios are all collective motion. So collective motion is basically just a movement information between them. Before talking about the motion, we have to talk about the navigation technology because currently nowadays, there are two trends of research. The first one is by using external peripherals or devices. Because each robot, when they want to move in formation with each other, they have to know and they have to determine their current location in 3D space or 2D. To accomplish that, some external devices must be attached to the environment. And the second one, that device may be the camera or the ultrasonic or the ultra-wideband module. And the second research trend is by using expensive sensors and some computational burden algorithms like the simultaneous localization and mapping, or in short, SLAM. To solve these two big problems nowadays, we have come up with our own robotic design. There are three big main features. The first one is the local processing. Each robot will only have to process in their internal microprocessors. They don't have to handle the external extra communications or anything like that, or we don't really need the external devices that I have mentioned earlier. The second one is our complexity is very small because here, as you can see, each robot will only have to measure the distance with 3 neighboring robots. So it's not a very big number. This leads to our third feature, that is the high scalability. Our system, we can add more robots into it, but we'll still able to accomplish the collective motion. So this is our basic theoretical basis, and we are using the AES model. So what is it? To say in short, the AES model main working principle is by imagining the imaginary spring forces between the two agents. Here, if they are too close together, they will be pushed out. And if they are too far apart, they will be attracted in. By doing this, each individual will be able to keep their distances with the neighboring robots, so the whole system will be moving in a synchronized formation. Here, as you can see, like this picture over here. However, we also do have some modifications to the model. We choose the hexagon formation, as you can see right here, and we introduce a new technique called turret synchronization. The turret up top right here, they will always maintain a fixed angle or a fixed heading relative to a predetermined direction, maybe north or maybe south. And we also introduce a new measuring technique. So for the two robots to measure the distances between themselves, as you can see right here, this is the IR receiver or infrared receiver. This is the infrared LED, and this is the ultrasonic sensor. So first, the LED on the robot A will pose a signal informing the second robot to start ticking the clock simultaneously. Then the ultrasonic here will send a sound pulse to the second robot, and after the second robot receives that pulse, it will blink the LED one more time to inform the first robot, and they will both stop measuring the time. And I think this equation down here is very comprehensible. Here, as you can see, These our robots consist of 3 layers, and each of them will have their own PCB, printed circuit board, to get rid of all the clunky wirings. Here this is the top PCB, this is the middle one, and this is the bottom one. This is our full product. And for the hardware components, the bottom layer is responsible for the motion of the whole robot, because there are 2 wheels right here. I can turn this robot here for you. There's a microcontroller to handle all of that, and also a power managing system for the whole robot. The second layer is used to implement the turret synchronization technique. It has the servo and IMU, inertial measurement unit. Lastly, the top layer is used for measuring the distance and handle all of the sensors and receivers right here. Our development process had gone through 4 stages out of 5. So first of all, we had to form our basic idea and our basic design. Then we split the design into small modules, and each of us will test and develop that module. And then we merge them all together. We finalize them. And for the 5th stage, we will be deploying and testing our AES algorithm, because this robot hasn't been implemented the AES algorithm inside yet. So here, as you can see, these are a few images about our development process. This is stage 2. And in stage 3 here, I assemble and I solder all of the components up top for the whole robot. And for the 4th one, I checked for all of the electrical failure or some miswiring in the PCB, and also I had to check for the overheat problem for the components, or will they explode or not. So as I said earlier, we haven't yet implemented the algorithm for this robot, but we have managed to come up with this little simulation that I think you guys will understand. Here, the robot will try everything it can to maintain a fixed distance with each other. Our swarm robots have a wide range of applications. First one, here, as you can see, a swarm of drones can be utilized to use for the search and rescue missions. The second one is a swarm of canoes can be utilized to measure the depth of the sea. And this is our further development. So this is the end of my presentation. I hope you guys enjoy it. Have a good day.